Josie, would you give me the vertices of this tetrahedron?
Yeah, it's 201.
Okay, wait, I'm going to, I hope we get the right one. 201, yes.
Yep, 530.
530, yes.
325
Yes.
and 153.
Okay. I'm going to try to see if I can get the pin the video on me so we're on the board. Nothing to do with you, Josie. Now, but these form a tetrahedron, and I'm going to draw a picture here, but it's not going to be accurate. It's just going to be for reference. 201, 530, 325, and 153. And we'll call this T for tetrahedron. And then the volume, to compute the volume, we'll integrate the one function over T. And this is a triple integral. T is a three-dimensional object, so this is a triple integral. And this in general will be an approximation. If we write this as an iterated integral, then in general, an iterated integral will be an exact value if you can find it. So this is iterated. And finding the volume this way would be triple. And the way Mathematica deals with these, this is this, integrate the one function over T, but you have to define T, which we could have done up here. Well, I think tetrahedron is a Mathematica command. So it's pretty easy to define T as a tetrahedron. And this does it. The real issue of this problem is not this triple integral business, but doing the iterated integral to do it exactly. And this process I'm going to show you will not only integrate one, it will integrate any function, and it will do it exactly. So over here on the left, that's what I'm going to do. And I'm going to begin by looking at, say, this vector right here that begins at 201 and ends at 530. So that vector U1 is 3, 3, minus 1. And I'm just going to do, I'm going to build up a parameterization, but I'm going to look at this one first. Alpha of t equals 201 plus t times 3, 3 minus 1, 0 less than or equal to t less than or equal to 1. And if you look at this parameterization, if t is 0, you're at 201. If t is 1, you're at 3, 3 minus, you're at 530 because you add these two. And then points in between, we'll go to points in between. So this is an exact parameterization of the line segment between these two vertices. It gets more interesting if I add a little bit more. So I'll get this U2 vector that's between 201 and another one of the vertices, say 153. So 1 minus 2 is minus 1. 5 minus 0 is 5. 3 minus 1 is 2. So minus 152 is that vector. And then maybe I add to alpha and make it a two-variable function, t times this plus s times minus 152. 0 less than or equal to s, t less than or equal to 1, and 0 less than or equal to s less than or equal to 1. Now, if I do that, you might think that this is the whole little face right here, but it isn't. But it's easy to figure out what this does parameterize. If I just look at these two vectors by themselves, U and say U1 and U2, if S and T can both go between 0 and 1, then you can, by taking T, say, to be a half, you would be halfway here. And then you can do anything in the U2 direction, or 1/4 anything. So if you let S and T go between 0 and 1 independently of each other, it gives the area of that parallelogram determined by those two, not the triangle. The triangle consists just of the left-hand side. It's exactly half. And to do that, to make it half, then rather than let S go between 0 and 1, you could let S be anything in the remainder after T has taken up some value. S can be anything between 0 and what remains. So if you do this, then you get just this half. So in any case, that is how to parameterize one of these faces. You've got 4 faces to the tetrahedron. So if you parameterize each face separately and integrate 1 over that face, you will get the area of the face. So if you do those 4 integrals and add them up, then you get the surface area. But I wanted to do a little bit more here. I wanted to add one more vector, U3, the vector between the remaining vertex and 2, 0, 1. U3 is 3 minus 2, or 1, 2, 4. And then if we add another variable here, plus P times, say, 1, 2, 4, with 0 less than or equal to T less than or equal to 1, 0 less than or equal to S less than or equal to 1 minus T, 0 less than or equal to P less than or equal to 1 minus S minus T. This will give the exact description of, this is a parameterization of the entire tetrahedron. And this parameterization is kind of what I was pushing for us to get. And this parameterization will let us do this integral pretty well. So I'm going to leave the parameterization and erase my pictures. So the iterated integral then of the 1 function, S will go between 0 and 1, T goes between 0 and 1, S will go between 0 and 1 minus T, P will go between 0 and 1 minus S minus T. Integrate with respect to P first, then S, then T. So this is the volume, except for the fact that I have left out the expansion contraction factor. So we're going to have to compute that expansion contraction factor due to this change of variables here. If you compute alpha prime of T, S, and P, you get a 3 by 3 matrix, since there are an X, Y, a Z, and an S, T, and a P. And if you work this out, the 3, 3 minus 1 that we used in the formula becomes the very first column. The second U2 vector, minus 1, 5, 2, becomes the second column. And the last vector, 1, 2, 4, becomes the last column. And this is just a matrix representation of this linear transformation. We have a 201 added on, but there's a linear transformation involved, and this is the matrix representation from it from linear algebra. So the determinant of this is what we want. So the determinant of alpha prime of T, S, and P, and that might be 5 if we work it out, I'm not sure. UC and I just worked on this a little while ago, and I think we got 5. But whatever this works out, Mathematica can find this. This is just a computation. And this is the expansion contraction factor, is always the same determinant of these U1, U2, U3 matrices. And then this integral is how to do the exact way. This will give you the exact value, even if you replace this by a temperature function. It will still give you the exact value. So this is the standard way to do exact integrals over tetrahedra. So now I'm going to end the video. I hope you are still there.